Let's talk about the graphs of polynomial functions. Now, the polynomials are a big family of functions with a whole lot of different sorts of structures that they can have. But their graphs all have certain features in common. We will not be developing all of the tools that we need to carefully graph every polynomial just at the moment. And the main reason for that is that we need either some unnecessarily complicated algebra techniques or some of the basic techniques of calculus to help us find some of these features. So for now, we're going to look at this graph and see what features we can understand. And by the end of this lesson, we will be able to not necessarily draw the graph of a polynomial given its expression, but we will be able to come up with an expression given the graph and the fact that it's the graph of a polynomial. So this graph has certain features that are common to polynomials. One of the things that we notice is that this function is what we call continuous, which means that if we wanted to, we could trace all the way along the graph without having to lift our pencil. There are no breaks or jumps, no points where the function is undefined. Now, one of the sets of points we see is points A, C, and F. These are the x-intercepts of the polynomial. Now at the x-intercept, that's where y is 0. So those x-intercepts occur whenever x is equal to one of the zeros of the polynomial. Okay, so that's one of the features of interest that we see on this graph. We already know everything that we need to know to find the x-intercepts. The points B and E are called local minima. One would be a minimum. Minima is the plural because we're in math class, so we all speak Latin. What we mean when we say that they're a local minimum is to say that their y-coordinate is less than that of all the nearby points. We know how to find those if we happen to have a quadratic. If we have a quadratic, that's just at the vertex. If we don't have a quadratic, if our polynomial has higher degree than that, we don't know the tools that we would need to find those right now. Similarly, point C, which we're mentioning again, point C is called a local maximum. So local minimum was the bottom of a valley. A local maximum is the top of a hill. Its y-coordinate is higher than the y-coordinate of all the nearby points. And then a feature that we see on almost every graph of a function that's real easy to find is point D here, the y-intercept. The y-intercept, that's just where x is 0. We can always find that. Just throw in x equals 0, see what happens. The last thing we see in this graph is what's called the end behavior of the function. That's what the graph does for very large values of x. So in this graph, we see that as we go off to the left or to the right, our y-coordinate gets very, very large. We go upward as we go off the graph in either direction. So the end behavior describes what f of x does for very large positive or negative values of x. For a polynomial, when x gets very large, positive or negative, f of x does too. Note, we haven't said anything about signs. one of the things that we're going to be able to do for a polynomial is predict its end behavior. That is, if x gets very, very large, does f of x get large positive or large negative? So those are the features to be aware of for the graphs of polynomials. And to a very great extent, though they're a large family, they all have a certain similarity of appearance. And after you've looked at a few of them, you start to look at a graph and think, you know, that looks an awful lot like a polynomial. And that's really our main aim here. It's to locate some of these features, understand what we're seeing, and to look at a bunch of graphs and get to a point where we can say, okay, that's probably a polynomial.